Hi, my name is Professor Mac, and welcome to my laboratory. Today we are learning about momentum. In physics and engineering, we use a quantity called momentum to predict the motion of objects which are in a collision, and to design systems such as rocket propulsion engines. Momentum of an object is influenced by its mass and its velocity. It has to have both to have momentum. Mathematically, we express momentum as the mass of the object times its velocity. So from this you can see the momentum of a stationary object is zero as a result of its velocity being zero. And you can also see the momentum increases as the mass increases or the velocity increases. A powerful concept is the conservation of momentum. This says that the total momentum before a collision equals the total momentum after the collision. This allows us to do some amazing calculations to predict the motion of objects after a collision. Let's have a look at an example of this in action. Welcome to my experimental test site, located in the beautiful hills of Scotland. I conduct experiments here to demonstrate the laws of physics. Today, I'm using the Mack lifting vehicle to load shipping containers onto a rail freight wagon for onward transportation. So the container is safely loaded onto the rail wagon. Oh no, there is another wagon moving towards it. Let's pause. What do you think will happen when it collides with the stationary wagon? Well, we can use the conservation of momentum to find out. Let's do the calculation. Here we have a view of the two wagons just before the collision. There are no brakes applied to either wagon, and we can ignore the friction between the rails and the wheels. Let's represent the mass of the moving wagon as m1 and its velocity as v1. We will represent the mass of the second wagon, which will include the container on it, as m2 and the velocity of the combined mass as v2. So the total momentum before the collision is given as m1 v1 plus m2 v2. Now we know the velocity of the stationary wagon is zero, so its momentum is zero. This means that the total momentum of the system before the collision is m1 v1. Now let's consider the total momentum after the collision. We will assume the two wagons become locked together during the impact. So the momentum of the objects after the collision equals the mass of the unloaded wagon m1 plus the mass of the loaded wagon m2 times the velocity of the combined mass of both wagons, which we will represent as VA for the velocity after collision. The conservation of momentum tells us that the total momentum after the collision is the same as the total momentum before the collision. So we can write this as m1 plus m2 times VA equals m1 v1. We can then rearrange this to give VA equals m1 divided by m1 plus m2 times v1. So there we have a very nice equation for predicting the velocity after a collision between the two colliding vehicles, where one is initially at rest and they are joined together after the collision. You can see that the velocity after the collision is simply the velocity prior to the collision multiplied by the ratio of the moving masses before and after the collision. Let's use this equation to understand more about the velocity of the two wagons after the collision. Conveniently, in this case, the mass of the stationary wagon with the container on it is twice the mass of the moving unloaded wagon. So we have m2 equals 2 times m1. And if we substitute this into the equation, we end up with the velocity after the collision equals m1 over m1 plus 2m1 times v1. We can simplify this by dividing through by n1, and this then gives us the velocity after the collision equals 1/3 v1. How cool is that? Without having any values for the masses or the velocities, we have established that the velocity after the collision is simply 1/3 the velocity of the moving wagon prior to the collision. Note that this relationship is specific to the situation where the mass of the stationary wagon plus the container is twice the mass of the moving wagon. Okay, let's see what actually happened. Wow, that looks just like what we predicted. The velocity of the wagons after the collision is around 1/3 the velocity before the collision. So we were able to use the conservation of momentum to predict what happened. Now, what do you think will happen if there was a fixed barrier on the track ahead of the moving wagons? Let's see. Well, the barrier brought the wagons to rest, as it is designed to do. However, if we applied the conservation of momentum to this situation, it wouldn't work, as there was clearly momentum before the collision, but afterwards everything is stationary, and therefore the total momentum is 0. Momentum was not conserved. Why is that? What is different between this collision and the collision between the two wagons earlier? Well, the conservation of momentum only works when there are no external forces acting on the system under consideration. The system we were considering for the collision between the two wagons comprised of the two wagons only. We had assumed the friction from the rails was 0, and therefore there were no external forces acting on the system. There were forces between the objects in the system as they collided. However, these internal forces do not affect the total momentum. Only external forces will change the momentum of the system. So what about the collision between the wagons and the barrier? You can see that the barrier is bolted down onto the ground, and therefore the ground provides a restraining force onto the barrier. The system of the barrier and the wagons therefore has an external force acting on it from the ground, and this results in a change in the momentum of the system. This is a very important point to note. The conservation of momentum is true only if there are no external forces acting on the system under consideration. So in summary, we learned that the momentum of an object is expressed as its mass times its velocity. And we have seen that the total momentum before a collision equals the total momentum after the collision. However, we noted this is only the case where there are no external forces acting on the system under consideration. If there are external forces acting, then there is a change in the momentum of the system. I hope you enjoyed learning about that. So from me, Professor Mac, until next time, all the best. Bye.